In this short video, we describe the BigDAWG polystore system. This work is sponsored by the Intel Science and Technology Center for Big Data. As we know, databases today are severely challenged by the volume velocity variety of big data. Enterprises are not immune to these challenges and often use a combination of databases and data models to support the types of analytics they wish to perform. While this may provide great performance benefits, this can often add complexity as users need to be aware of data locations, different query languages, and APIs. In order to alleviate some of these challenges, we are developing the BigDAWG system that promises to provide as much location transparency and semantic completeness as possible. BigDAWG is a polystore system that provides a federated database system for multiple disparate data models, database, and storage engines. As a polystore, BigDAWG aims to provide location transparency, semantic completeness, and relations between user semantics and back-end database and storage engines. In designing BigDAWG, we have adhered to a number of core principles. The first design principle is to support many sizes. We believe that there will never be any one-size-fits-all database, and that BigDAWG must be able to support heterogeneous storage and database engines. The second design principle is that the analytics of the future, such as those making use of the Internet of Things, will need to support real-time, low-latency analytics. Thus, BigDAWG must support streaming databases. The third principle is that users want to operate on data without explicit knowledge of location. Thus, BigDAWG must be able to support location transparency without compromising efficiency or performance. Finally, different databases and storage engines provide a wide number of operations. BigDAWG must support these operations, again, without compromising performance or efficiency. Implementing these principles requires the notion of what we call semantic islands. An island has a data model, a language, or set of operators, and a set of candidate database engines. In the exemplary figure, BigDAWG may consist of islands such as an array island, relational island, or other arbitrary islands that support certain types of queries or data models. An array island, for example, may be able to talk with a particular set of database engines using a language such as array query language. Using BigDAWG, a user specifies an island under which they wish to execute a query. By specifying the scope of an operation, users have full control on the mechanics of how their query is executed. For example, one may issue a query using a relational scope to perform an average, or use an array scope to issue a multiplication of two database arrays. To move data between engines, a user can also cast data between engines. In the island model, islands do the intersection of engines, whereas BigDAWG does the union of islands. Further, while we do support physical islands, most islands are logical and abstractions. Recently, the ISTC group developed a prototype of the BigDAWG polystore system and showcased how BigDAWG can be used to develop complex medical analytics. This prototype was developed with support from research groups across 7 universities and Intel. In the remainder of this video, we will describe how the BigDAWG polystore system can be used for medical big data. Developing such analytics requires deep knowledge of databases as well as medicine. BigDAWG aims to remove the prerequisite of deep knowledge of databases in order to allow medical researchers an intuitive single point of entry into the complex world of data management. Using BigDAWG, a medical researcher or clinician can quickly learn the details of a dataset and apply his or her medical knowledge to extract insight. The BigDAWG prototype makes use of a number of different islands to showcase how we envision the BigDAWG system being applied to complex heterogeneous workloads. In this implementation, we support D4M, an associative array island, Myria, an iterative island, and Streams, an island for the streaming database SStore. Further, to realize the transparency semantic completeness trade-off, we also support a number of degenerate model islands that provide. The first screen is the Mimic Explorer screen. This screen utilizes BigDAWG to connect to a relational database, Postgres, and an array database, SciDB. Using this screen, a medical researcher can get a high-level picture of the dataset and determine future queries. This screen uses the relational island for query execution. In the example shown here, you can set certain filters to look through the dataset to find patients of interest, find out about their stays, any text notes, etc. The next screen to utilize the BigDAWG polystore system is the text analytics screen. The Mimic dataset consists of a number of text notes such as doctors' and nurses' reports. However, it is often difficult to find notes of interest. This screen uses the D4M island for executing the query, which relies on non-negative matrix factorization for topic modeling of different patient notes. In this example query, we select patient and other parameters. The left half of the screen uses BigDAWG to connect to Postgres to get the raw notes and topics. On the right side come from Apache Accumulo and Graphulo to perform the non-negative matrix factorization on the dataset. highlighting the topics show you important pieces of the notes that might be of interest. The next screen utilizes the Myria island to perform an analytic on the dataset. The analytic of interest here is in determining the hemodynamically similar patients, or patients with similar waveforms. Such an analytic can be used to find similar patients in order to determine suitable treatment options. In this example, we take the discrete wavelet transformation of different signals and compare them across different patients in order to find patients who are similar. We also present various execution strategies in order to reinforce the idea that very often multiple data stores used in conjunction provide higher efficiency and greater performance, as we see here. Using SciDB only takes more time than Myria, but using a combination of SciDB and Myria can actually lead to better performance. The final screen we present is a streaming data analytic that utilizes SStore, or streaming database. We believe that real-time analytics will play an important part in future workloads. Here we use a streaming island to look at incoming waveforms through BigDAWG. As alert criteria are created, potentially from the other screens, they can be registered through the BigDAWG polystore middleware. You can also look at details of each waveform. This operation uses BigDAWG to talk to a relational database and the streaming island to talk to SStore.